Johnny here with Simpson Math. In this video, we're going to introduce logarithms, very quickly look at its graph, but the focus will be on the definition of the logarithm, and that is how to convert something we're familiar with, the exponentials, into logarithms, and then vice versa. And then a few examples doing that, where we can simplify and maybe get some values. And to do that, what I would like to do is first start off with a graph of the logarithm. Just what is a logarithm? And they come from the exponentials. So here I have our graph from a previous video. This is just y equals 2 to the x, the exponential function. And we discussed last time all this information. So if this information is new to you, you may want to go back and check out that previous video. But here I have 2 to the x. And we call this a function because it does pass a vertical line test, meaning every x value has only one y value. And functions that then go on and pass a horizontal line test are called one-to-one functions. So I'm going to take a look at my function here. And it does pass a horizontal line test. It gets a little bit tricky here with the horizontal asymptote, y equals 0, but this function does always decrease. It just never hits 0. It passes the horizontal line test, meaning every y value only has one x value. So this y value of a half only has one x value of -1. And we know one-to-one functions have inverse functions. So this exponential graph, this exponential function, is a one-to-one function. So there is this inverse function out there. We also know, given a graph of a one-to-one function, that we can very quickly graph its inverse function. Because inverse functions just take your inputs and your outputs and interchange them. Your x's and y's are interchanged. Your domain and range are interchanged. Any y's become x's, and vice versa. So, in a different color over here, I'll call this f inverse of x. I'm not sure what the function is quite yet, but I know there is this inverse function out there, and I'm going to get some points and then plot them on my graph. So, I'm just going to take the values I already know from my exponential function, my x's and y's, and interchange them. So instead of -2 mapping to 1/4, 1/4 will map to -2. 1/2 maps to -1. 1, 0, 2, 1, and 4, 2. These are points on the inverse function. I'm going to graph these points. At a quarter, I get -2. At a half, I get -1. 1, 0. So instead of a y-intercept at 0, 1, we have an x-intercept at 1, 0. 2, 1 is a point, and 4, 2 is a point. And hopefully with these points, you can start to see the shape of this inverse function of the exponentials. Instead of having a horizontal asymptote at y equals 0, we now have a vertical asymptote at x equals 0. Let's see if I can graph it the best I can. All right. Now, everything has been swapped. So the domain, I have a new domain now. And just looking at it, I can see I've got no negatives. I'll never touch 0. So I must start on the positive side of 0 and then go out to infinity. And notice that was the range of my exponential. Because the domain and range, those are x's and y's, and they've just been interchanged. So the range of this inverse graph will go all the way down to -infinity, all the way up to positive infinity, So I'm just going to write all real numbers, -infinity to positive infinity. We'd have a nice point of interest, this x-intercept. That's at 1, 0. We have a vertical asymptote at x equals 0. And this pink graph, or this graph, is the inverse of the exponential. This is what we call a logarithm. Logarithms are functions. This passes the vertical line test, and they are the inverses to the exponentials. All right. Now, one big panic button maybe is to notice that their domain is restricted. We'll talk more about this in maybe a later video, but whenever we talked about even root functions like the square root function or the rational functions, 1 over x, or the x is in the denominator, we made a big deal about their domain because their domain is restricted. Exponentials have no problem, but the logarithms do have a restriction on their domain. They seem to be positive, not 0, not negative, only positive. All right, so there's what a logarithm looks like, maybe where it comes from. I guess while I have your attention on this graph, I'll go ahead and tell you what this function is. This would be the function log base 2 of x. Hopefully the definition that I'm about to say or spit down will make some more sense of it. All right, to continue on with logarithms, you've got to know the definition, and that is how to take an exponential and rewrite it as a logarithm. For the remainder of your life in your math career, you've got to know this definition of a logarithm. So here we go. It says, if you have some sort of exponential expression, you've got some base being raised to some power, and that equals something. And we're familiar with this. 2 to the third power is 8. 5 squared is 25. Just some sort of exponential expression. It is equivalent to, or it can be rewritten as. This double arrow means it goes backwards and frontwards. It just means I can rewrite it as this other thing. Exponentials can be rewritten as logarithms. I'm going to use log, short for logarithm. Log. Now, as soon as you say a log, you really should say the base. This log has a base b. Just like the exponential has a base b, the log has the same base b. It's a little subscript bw. Of the other side of the equation, of m in this case, is equal to our power p. So b to the p equals m can be rewritten as log base b of m equals p. We call m, or what's inside these parentheses, the argument of a log. It's very similar to back in the day when we were square rooting. If I wanted to say the square root of something equals something else, I would put that under the radical, the square root of 25. I want log of m. If you're squaring something, or let's put a square there. If you're squaring something, it's that thing is being squared. Those are arguments. It's what's going on inside those parentheses. All right. Cool. Let's see if we can just do one crazy, silly example real quick. If I have a circle, in fact, let's make it a sun, so it's obviously not a 0. I raise the sun to a moon, crescent moon, and that's equal to a star. I want to rewrite these symbols in logarithmic form. Definition says that's okay. you'd say log, and then as a subscript or small script, you write the base. So my base is this sun symbol of star, and that's equal to moon, the power. Cool. All right, let's see. Are we ready to just get straight into some examples? I guess so. Let's just jump straight into it. All right, first we'll start off with, given a logarithm, rewrite it as an exponential. So I'm given this log base 2 of 64, and that is equal to 6. And I'm going to rewrite that as something I'm more familiar with, the exponentials. So I'm going to say this is equivalent to, using my definition. So I'm just going the other direction now. I'm saying I've got a log, and I'd like to rewrite it as an exponential. Well, I think I'll start off with that base. Log has a base of 2 here, so I'm going to say my base is 2 in the exponential. 2 is being raised to the 6th power, and that equals the argument, in this case, 64. And this is a true statement. 2 to the 6 is 64. So something I know to be true, I can rewrite in logarithmic form. We say in English, these symbols right here, log base 2 of 64 is 6. Practice that. Log base 2 of 64 is 6, or is equal to 6. All right, let's do another example. Let's take a look at 3 equals log base b of 27. My 6's and b's may look similar, but this is above I was using 6's, now I'm using b's. This is 3 is equal to log base b of 27. Right now that is in logarithmic form. I have some log equaling some powers. That 3 is just the power. I'd like to rewrite in exponential form. You try. So I get base b being raised to the other side of the equation, 3, and that's equal to the argument, 27. So b cubed equals 27. Now let's see if we can go the other way. Given an exponential, can we rewrite it in logarithmic form? So I have been given 5 to the 4th equals 625. That's a true statement. But I want that in logarithmic form. So I'm going to start off with log base 5 of 625, and that's equal to the power 4. Something to notice, these logarithms are just the powers. Logs are just powers. Logarithms are the inverses of the exponentials, but logs, at the end of the day, they're just the powers. They're like exponents. Let's try that again. I think I'll amp up the difficulty level just a bit. I'm going to be testing your old exponent rules. Keep them fresh. So my base is 5. I have a power of -3, and then that's equal to 1 over 125. I'm going to rewrite it as a log. Nice and simple. I introduced the logarithmic notation. The base is, again, 5. The argument here is the other side of the equation, 1 over 125, and that is equal to the power -3. How about the cubed root of 64 equals 4? Yes. What you got? We may need to rewrite this as a power first. I don't quite see the power yet, so I'm not doing any sort of logarithmic talk yet. I'm just going to rewrite what was given to me. This is 64 being raised to a 1/3 power. Now that I've rewritten it as a power, like a base being raised to a power in exponential form, I feel comfortable rewriting it in logarithmic form, where I have log base 64 of 4 is equal to the power 1/3. All right. In the homework, there's going to be some practice going back and forth, Just get real comfortable with this. All right, now we're going to go a little bit further, and that is the same idea. We're going to use this definition of the logarithm to start to evaluate or simplify what we have been given. So here we were given log base 7 of 49, and we want to simplify this, or maybe evaluate it. It's like if we had said, evaluate the square root of 100. That square root symbol means there's something to do. Let's do it. This log notation, there's something to do. Let's do it. Sometimes you can't simplify it, like the square root of 3. There's nothing to do there. We leave it as a square root of 3. So there are some logs that you'll just leave as logs because they're just not pretty. Well, let's start off today with some pretty ones. All right. If I was given this expression, log base 7 of 49, I would say, hey, this logarithm should be equal to something, some power over there. So what I kind of want to do is introduce a variable, maybe a question mark, but this is equal to something. What is it equal to? By introducing a variable, you can put an x there. I have this logarithmic equation, and I can rewrite that in exponential form. So I'm going to use the definition here, where my base is being raised to the other side of the equation, and that is equal to the argument of the logarithm 49. So this simply just restated now says 7 to the what power equals 49. I think we know that. This is equal to 2. So there's two ways to answer this question. If I said, what's the square root of 100? You would just say 10. So I just kind of want to say 2. But if I said, what's the square root of 100, and you put an x in there and tried to solve it, in the end, you said x equals 10, then x equals 10 is your answer. So if you introduce a variable, you can say that's your answer. But log base 7 of 49 is simply 2. I hope that makes sense. Let's do some more. How about log base 3 of 27? Well, this is equal to something. This time I'll use a variable, x. I'd like to know what is that equal to. So I'm going to rewrite this logarithm in an exponential form. Base 3 to the x power equals 27. And this I just know. 3 to the second power is 9. 3 to the third power is 27. So this is simply 3. Or you could say x equals 3. Let's try something tricky. Log base 6 of 1 over 6 equals x. I want to know what x equals. Right now it's in logarithmic form, so I think what I'll do is kick it over into exponential form, something I'm more familiar with. Base 6 raised to the x power will equal the argument 1 over 6. And then what power would take my 6 and reciprocate it, kick it down into the denominator? A negative 1 will do that. Log base 6 of 1/6 is negative 1. Let's try log base 3 of 1 over the square root of 3. Okay, well, these logarithms are powers. So that square root of 3, I think I want to represent that as a power. I'm not going to go to exponential just quite yet. I'm just going to first change that square root notation into a power. That'd be a power of 1 over 2. So I have log base 3 of 1 over 3 to the 1/2 power. Just to help me visualize what's going on. Now I feel comfortable rewriting this in exponential form. 3 to the what power is going to give me that mess? 1 over 3 to the 1/2 power. Any ideas? We said earlier that the negative exponent will take the 6 and kick it down into the denominator. So that's happening again. 3 is definitely being raised to a negative number to kick it down below, but it's also being raised to a 1/2. So this is a negative 1/2 power. And we can just test ourselves just to make sure. If I said I had 3 to the negative 1/2, and someone asked me to simplify this, I would take care of the negative aspect first. 3 to a negative number is simply 1 over 3 being raised to a 1/2 power. Oh, and the 1/2 power is notation for square root, or we use the square root notation. Oops. So I'm happy with this. All right, practice, practice, practice. Let's see what else I can give you. Let's do log base 11 of 11. So I'm going to convert it over to exponential. Maybe I can start to do that mentally now. This is saying 11 to what power would give me 11? Do that one more time. This is equal to something in exponential form. That is, the base of 11 is being raised to x, and that is equal to the argument 11. So 11 to what power is equal to 11? Okay, I think it's got to be 1. I would call this an identity property of logarithms. If your base ever matches your argument, it's always going to be set up like this, so it's always going to be 1. I'll just go ahead and write that down. Identity property. I claim if you just memorize the definition and always use the definition, you're fine. But if you see this a few times, you'll start to recognize, oh yeah, that's just going to be 1. So if you have any base to the first power is equal to the base, so that's in exponential form. Rewriting that in logarithmic form, I have log base b of b equaling 1. Exponential form, b to the power equals b. So I put it in logarithmic form, right? Log with my base b of the other side of the equation is equal to my power. All right. So bases of our match argument, it's just going to simplify down to 1. Let's do another example. Something like log base 6 of 1. Rewrite it if you need to. I'm going to try to do this mentally real quick. 6 to the what power would give me 1? 6 to the what power would give me 1? Now this is an exponent rule I'm just kind of supposed to know. Any non-zero number raised to the 0 power will spit out a 1. So 6 to the 0 power is 1. I would call this maybe a 0 power property, where if you ever have an argument of 1, the way we get that 1 using exponents is an exponent of 0. I'll go ahead and write that down too. Again, this comes from the definition of logarithms, so if you just know the definition, you don't need to know like these properties, but I'm just going to write them down for fun. That b to the 0 equaling 1, some base other than 0, base of 0 power equaling 1. Then when I rewrite it in logarithmic form, I'll have log base b of 1 equaling 0. What I'm trying to say here is, if you ever have a log, with whatever base you put down here, if your argument is 1, it's always going to be 0. All right, next example. I have log base 4 of 4 to the 6th power. This is in logarithmic form. I'm trying to mentally ask myself the question, 4 to what power is going to give me 4 to the 6th power? Okay, I think I just answered my question, but I'm going to go through the steps. Here I have a logarithmic equation, and I'm going to rewrite it as an exponential equation. Base 4 being raised to what power will give me 4 to the 6th power? Well, if this equation is true, and my bases are equal, then that x must be equal to 6. 4 to the 6th power would be equal to 4 to the 6th power. So I claim it's x equals 6. I think this is going to work no matter what those bases are. So if I said log base 5 of 5 to the 7th power, I think I can just use this knowledge to quickly answer this question. 5 to the what power would give me 5 to the 7th power? Well, this is going to simply be 7 in the end. All right, let's take a look at something like this. 7 being raised to a logarithm, log base 7 of 23. Here's a question for you. Is this in logarithmic form or is this in exponential form? This is in, right now, exponential form. I've got a base being raised to a power, and it's equal to some value. So, to answer this exponential situation, I'm going to rewrite it in logarithmic form. Using the definition of the logarithm, I can take a exponential equation and rewrite it as a logarithm or logarithmic equation. I get log. What's my base? 7. What's my argument? The other side x. And that's equal to the power log base 7 of 23. Oh, look at this. If this equation is true, the log base 7's match. If that equation is true, that x has to be 23. This and the previous one, where the base matched the argument, and this one where the base matches the base, I call these inverse properties of logarithms. And the more you see them, the more comfortable you are just quickly simplifying. But notice, given 7, log base 7 of whatever, these 7s clue me in that I'm going to be left with whatever that argument is, 23. So a quick little example, if I had 3 log base 3 of 10, I know since my bases match, in the end I'll be left with 10. It comes from the definition of the logarithm. I highly recommend you practice that over and over and over again. But do it enough times and you realize, oh yeah, these bases match. In the end, I'll just get 10. I call these inverse properties. So let me write them down real quick. Log base b of b to the x is simply x. B being raised to log base b of x is simply x. All right, a few more little things to talk about, and that is the common log, or an understood base. So every time I've mentioned the log, I've always said the base. If I say log of 2 and I leave off the base, well, there's an understood base of 10 when using logarithms. So we just kind of write that down. If the log has a base of the irrational number e, we call that a natural log. This is ln. Most textbooks and people, when they write log and ln, they'll use cursive. Just because, like my notation here, it almost looks like I say 10g, which is very misleading. So really, when you write logs and natural logs, you should kind of use like a cursive log or ln, but I stick with my script. So ln, which is the natural log, has an understood base of e. ln and log, it's the same notation, it's just log. So the definition still applies, but if I write log, the understood base is 10 unless I tell you otherwise. ln is a log with a base e. All right, here we go. Let's do some examples. Log of 1,000 equals x. I'd like to simplify this. Log of 1,000 equals x. Notice I left off key information. I didn't say the base. But if I leave that off, then it's understood to be base 10. So this is simply saying 10 to what power is 1,000? Well, 10 times 10 is 100. 10 times 10 times 10 is 1,000. So this is 3. Let's try log of 10 to the 8th power. Oh, I claim this is an inverse property. I have a base matching a base. My understood base for log is 10. So this matches. So in the end, I should just get 8. But maybe I'm not comfortable with that just quite yet. So I just want to use the definition. This is equal to something, so I can rewrite it in exponential form, where I say the understood base of 10 raised to the other side of the equation is equal to the argument 10 to the 8th. Now I can clearly see in this exponential form, if these two things are to be equal, then that question mark has got to be 8. So if you're ever not 100% sure, use the definition. The definition is how to go. How to do. All right, let's see how tricky I can get. Let's take 10 and raise it to log 53. Well, I did not mention the base, so it's understood to be 10. These 10s are matching. This is this situation. I've got a base being raised to a log with a matching base. So in the end, this is just going to be 53. If you don't see that, use the definition. Rewrite it as a logarithm, and then it'll be clear. Oh, the first time I'm using the natural log notation. Ln, natural log. It's just a logarithm, and it's going to be equal to something. I'll put a little question mark over here. And I say, okay, well, the base is e. Whenever you have a natural log, the base is e. So e, let me use like a little green here to clue in which e I'm talking about. My base e is being raised to something, and that's going to give me the argument of this natural log, e. Oh, yeah. This is just going to be that identity property. This is just 1. E to the first power gives me e. All right, let's take a look at the natural log of 1 over e to the 7th power. I think I could just do this in my head, maybe. This is saying base e raised to what power would give me 1 over e to the 7th power. Two things are going on. I'm spitting up a 7 up there, and also I'm reciprocating. So this is just going to be negative 7. Another natural log with an understood base e of e to the 13x. My bases are matching. This understood base e is matching the base within inside the argument. This is simply 13x circle. Let's move on. Next example, e to the natural log of e of 7x squared. Again, my bases are matching. E is being raised to a natural log base e I can use the definition, but I know this is just going to simply, in the end, be 7x squared. Circle it, let's move on. (10) raised to log of the cubed root of x. Again, my bases are matching. Log has an understood base of 10. In the end, I'm just going to get the cubed root of x. I just used inverse property, an inverse property, an inverse property. Here, I just did it mentally. It's got to be negative, and it's got to be 7. Up there, I used an identity property. I don't want you to focus in on trying to memorize these rules. What I want you to do is memorize the definition and apply it. Use the definition enough times, and you'll see these patterns. All right. I think that's it for the introduction to logarithms. So have fun converting logs to exponentials and exponentials to logs, and simplify. And I'll see you in the next video.